Greetings and salutations, magical chemists. Today let's talk about VSEPRs, otherwise known as valence shell electron pair repulsion theory. This is what allows us to predict the three-dimensional geometry or the shape of molecules. It turns out it's relatively straightforward to predict the geometry simply based on the known fact that electrons repulse each other. And so when you have differing groups of electron density surrounding a central atom, either from bonding or lone pairs, they're going to try to be as far apart as possible and thus minimize the repulsion. It's important to recognize that as far as VSEPRs is concerned, double and triple bonds are treated the same as a single bond in terms of their ability to repel electrons. Okay, so multiple bonds and single bonds are treated the same. However, it is important to recognize that lone pairs are going to have a greater magnitude of repulsion than bonding pairs. And why is that? Well, it has to do with how many nuclei each pair of electrons is attracted to. Lone pairs are basically stuck on a single atom, a single nucleus. But bonding pairs are attracted to two different nuclei, so they're kind of stretched between them. That means the lone pairs have basically, it's like a more concentrated electron density up close and personal with that nucleus, and so they end up having a greater repulsive effect because they're taking up more space. So let's see the significance of this effect by looking at a couple of examples. If we compare methane, CH4, ammonia, NH3, and water, H2O, we have basically three structures that have a tetrahedral electron geometry. They all have 4 locations of electron density. But notice, when all of those regions are the same, they're all bonding pairs like in methane, well, then there's a very symmetric bond angle between any of the carbon-hydrogen or hydrogen-carbon-hydrogen bonds. It's 109.5. But when you go to ammonia, this lone pair that's hanging out over here tends to push these a little bit further away, so they get closer to each other. It means the HNH bond angle is about 107. And water, of course, has 2 lone pairs in the central oxygen, which have that even more repulsion pushing those 2 hydrogens together. So now it's got an even smaller bond angle. So there is a definite and noticeable effect from the increased repulsion of the lone pairs. Okay, I was throwing around some terms there, the regions of electron density or electron domains. It's important to distinguish between electron domains and bonding domains. Okay, so electron domain is just a fancy way of talking about regions of electron density around a central atom. Whereas a bonding domain is, well, you guessed it, regions of bonding electron density around a central atom. So there are technically 2 different geometries you're going to be expected to find. There's something known as the electron geometry, which is based just on the number of electron domains. And then, of course, there's the molecular geometry, which is just based on bonding domains. That's what gives you the valence shell electron pair repulsion, or VSEPR shape. But the reason that we want to use electron geometry as well is it allows us to predict something just as important: bond angles. And yes, it's not enough to know the three-dimensional shape or molecular geometry of a given molecule. You have to be able to predict the angles between the atoms as well. And that's why electron domains can be a very powerful tool. Okay, so as far as counting electron domains, basically, if you've got a lone pair, a single bond, a double bond, or a triple bond, that's each one domain. Yes, I totally said it, and it's true. Single, double, or triple bonds, remember, we're pretending they have equal repulsive effect, so they each count as just one electron domain. Well, a bonding domain is all of those things except not a lone pair, because it's got to be bonding. So either single bond, double bond, or a triple bond counts as a bonding domain. But again, single, double, and triple bonds, just one bonding domain. So now that you have that information, you can use it to determine not only the molecular geometry, but also the electron geometry. So if you look at ammonia again, NH3, if you're counting the regions of electron density, well, there are 3 bonds, so those are 3 regions, but there's also a lone pair. So there are 4 regions of electron density, which means 4 electron domains, which means it has a tetrahedral electron geometry. However, it only has 3 bonding domains, which makes it trigonal pyramidal as far as its VSEPR shape. Something that's really convenient to note, if lone pairs are not present on the central atom, molecular and electron geometries are going to be the same dang thing. And expanded octets, which have all sorts of fun geometries. Lone pairs actually have two possible locations. There are the axial positions, and there are also the equatorial positions. So they're just what they sound like. The axial positions on the top and the bottom, and equatorial, like the equator, are the ones around the center. The trick is you have to know the bond angles, so you can place the electron pairs wherever they will be farthest apart. Okay, let's try, before we actually start looking at these specific shapes, geometries, what have you, let's just try practicing identifying the number of electron domains and bonding domains, because if you can do that, you can do anything. Okay, first one, we want to know the number of electron domains. We're looking for any regions of electron density. Well, lone pair counts as 1, 2, 3, 4. But for bonding domains, remember that lone pairs don't count. They're not participating in bonding. They're not shared. So there are only 3 bonding domains. All right, I would like you to try to do the exact same thing for the water molecule and for this formaldehyde over here. It'll be totally non-toxic, I promise. Whenever you're ready to check the answers, go ahead and unpause the video. Okay, first for water. Notice there are 2 bonding domains, but then there are 2 more lone pairs for a grand total of 4 electron domains. For number 3, for formaldehyde, for the number of electron domains, well, you have 1 single bond, another single bond, and a double bond. The lone pairs don't count because they're not on the central atom. Only the central atom is what matters here. So we have 3 electron domains and 3 bonding domains. They are the same thing. Okay, now that you've got that idea, let's take a look at all those wondrous shapes and bond angles that you're going to need to know. And yeah, I did say you're going to need to know them. It is the shapes and the bond angles that you absolutely must know. Now, in the past, some teachers, and me included, have said things like, well, okay, so if a trigonal planar molecular geometry has approximate bond angles of 120 degrees, if you have a trigonal planar electron geometry, but there's a lone pair repulsing it, a lot of people would just be like, oh, that's just less than 120. And in fact, that's even what your TRO textbook does, which is why the font is a little bit different. But the AP chemistry test is actually looking for you to put a specific answer. If you just say less than 120, that could be 5. 5 is less than 120, and it's definitely not 5. So what we're going to do is we're going to say rule of thumb, and this is on average pretty accurate. Every lone pair causes you to lose 2 degrees from your bond angle. So that's why we would say the bond angle on something like SO2, which has a lone pair, and then the 2 oxygens, is going to be about 118 degrees. It's not quite 120 anymore, despite its electron geometry. But now, okay, officially, you don't even have to know. Like, you don't have, no, AP does not have, like, there's not going to be a multiple choice saying, what is the electron geometry of blank? So officially, all you have to know, molecular geometry, bond angles. But the thing is, it's really helpful to know that the electron geometry is trigonal planar, because that's how you figure out what the bond angle is. If you can do it without that, if you just want to memorize, heck, I won't stop you. But I hate memorizing, and I'm really bad at it, and this is a really long list. So for me, I'd rather figure out the electron geometries and use that to reason out the bond angles. But you do whatever works for you. Notice, whenever there are no lone pairs, electron geometry and molecular geometry is going to be the same thing, and that's going to be true across the board. Okay, so the first part of this chart is looking at the non-expanded octets. These are the things that you have definitely seen before in pre-AP. However, when you look at the expanded octet, some of you have, but most of you have not actually seen all of the expanded octet molecular geometries. So not only is there octahedral and trigonal bipyramidal for when we have 5 and 6, but there's things like seesaw and T-shaped and square pyramidal and square planar. And, well, linear, but we've seen linear before, just not in that context. So notice, some of you will be learning some tasty new shapes. Don't worry, in class we're going to be building all of these so you can see where the repulsion comes from. Now, we do need to fix just a couple things, because you'll notice I went through and I tried to edit the bond angles that said less than blank, but haha, I missed some. So let's go ahead and just fix some of our bond angles so none of them say less than this amount. They have a more specific value. Now, depending on the different structure, these values aren't exact. Like, is SF4 have bond angles of exactly 118 and 88? Yeah, I don't know. But I do know it's close enough based on the range they give. So on AP free response problems, or if you're looking at a multiple choice, if you know these values, which again, totally not going to memorize, you're just going to figure out, okay, now the one thing, and we're going to look at this when we build them for trigonal bipyramidal, it's the only one that has two different bond angles. The reason is there's these two axial positions on the top and the bottom, and then there are these three spokes of a wheel, and that's 120 degrees between the spokes of a wheel, but it's only 90 degrees between the top ones and the ones along the equator, the quote-unquote axial versus the equatorial positions. But hopefully when you see that in real life, it'll make a little bit more sense. But make sure you're aware that there are two different bond angles going on in anything that started with a trigonal bipyramidal electron geometry. Okay, well, I guess that's not 100% true, because technically, once you get down to T-shaped and linear, there aren't enough positions left. Because remember, the electrons want to be as far apart as possible. So in T-shaped, I know they look like they're 90 degrees, but remember the repulsion, so they're about 86 degrees apart. And then when they're linear, well, haha, you win. They actually are just straight up 180 degrees apart. And then we have just one of them that we need to fix the square pyramidal, when we're looking at things that have an octahedral electron geometry. In this case, we've replaced one of the bonding pairs with a lone pair, and thus we're decreasing the bond angle just a little bit. Square planar is actually 90 degrees because, although you can't really tell from the way it's drawn here, technically you've got a lone pair up top and a lone pair on bottom, so the repulsions cancel, so everything actually is, square and a plane. That's why it's square planar. Okay, I know that's a lot of information, but it's definitely very regular patterns, and hopefully a lot of it is stuff that you've seen before. So let's look at one more thing before we do some practice. Three-dimensional shapes. Okay, now, first things first, you don't have to recreate this yourself. No one's going to say, using this three-dimensional drawing strategy, draw trigonal bipyramidal whatevers. You won't have to. But you will probably see example problems where this shows up, and honestly, I just like this. It just makes sense, because when you draw something tetrahedral, when you draw it like this, it just looks weird. It looks like the three things at the bottom are squished together, and the one at top, why is it all by itself? It's hard trying to represent something three-dimensional on a two-dimensional paper. So what we do is so there's this thick wedge. That means this is coming towards you in space. That's really hard to see with the highlighter. But then the hatched one, that means this is going away from you in space. So it's just trying to help you visualize what's going on. This is actually used a lot in organic chemistry. So if you think organic chemistry might be in your future, this would be a fun thing to look at. But you don't have to know how to do this. You just have to, not freak out when you see it. Okay, so let's go ahead. Let's try just a couple of practice ones together. And then you will be done with this video. Gasp, it'll be true. Okay. Before you can do any of this electron geometry, molecular geometry jazz, you are going to need to be able to draw the Lewis dot structure, which is perfect because that's what we've been doing all along. So take a moment, and I would like you to, pause the video, draw this delicious Lewis dot structure, and then when you are ready to check your answer, unpause the video. Okay. So hopefully you realized that to have a full octet, we needed a double bond between the carbon and the oxygen. As far as the Lewis structure is concerned, there are multiple different ways that you could draw it correctly. If you draw it like this, you are not wrong. That's a totally valid Lewis dot structure. However, I don't recommend it because the reason that this particular shape is the way that I will draw it, and that I will encourage you to do so, is because it kind of shows you, hey, the bond angle. It's showing you the electron-electron repulsion, pushing those three groups of electron density apart. So yeah, I'm already giving away answers because yes, 3 groups of electron density means that there are just 3 electron domains. So the electron geometry here must be trigonal planar. There's three things, and they're flat like the plane of a paper because there's nothing to repulse them. Conveniently enough, because there are no lone pairs on the central atom, there are still just three bonding domains, so the VSEPR shape is the same, trigonal planar. Notice, I know there's a lot of names to learn, but they kind of speak to the shape, because tri, of course, is a prefix that means three, and there were three regions of electron density and three bonding domains. So it makes sense it should start with trigonal. Okay, let's try two more examples, and then I will set you free. Of course, before we can do anything else, we need a Lewis dot structure, so pause the video, draw a tasty Lewis dot structure for hydronium, no flashbacks here, and when you're ready to check the answer, unpause the video. So here's hydronium. Remember, the positive charge meant that oxygen, the central atom, lost an electron, giving it one more single electron free to bond with another hydrogen. All right, I would like you to try these because, yes, you are that awesome. So whenever you're ready to, not scribble all over your paper, but actually, answer things, then, just unpause the video when you're ready to check your answer. In this example, there are 4 electron domains, 3 bonding domains, and 1 region of just lone pair electron density. Well, the prefix for 4 is tetra, so this is a tetrahedral electron geometry. But since there is a lone pair in the central atom, we now have a different number of bonding domains. There are only 3 bonding domains. Remember, the prefix for 3 is tri, so this is going to be a trigonal shape. But this is not trigonal planar. It's the repulsion from that lone pair is pushing these away. So this is trigonal pyramidal. I realize I've been skipping a step. Gasp! We're supposed to be putting in bond angles. Oh no. Luckily, that's quick and easy because I know the electron geometry. So the electron geometry is tetrahedral. Now tetrahedral means like if everything was identical, the bond angles would all be 109.5. But can't forget about that pesky lone pair. Remember, it's going to push them just a little bit closer together than they were. Because of that, we say it knocks off about 2 degrees. So we tend to say that the bond angle for hydronium would be about 107. I don't know why it's not 107.5, it's just 107. If you put 107.5, you would still be within the range. You would be fine. But I don't know, it's just a thing. People say 107. All right, so let's go back to formaldehyde because I totally forgot to do a bond angle on that one. But remember, if I know the electron geometry, the angles are easy. Trigonal planar, well, they're all flat in a plane, and you've taken your 360 degrees, your full circle, and divide it into, 3. So that means the bond angle must be 120 degrees. Okay, now that we've fixed that part, let's do one last example before we run on upwards and sideways to the next video. Oh, here's a fun one. It's a big pile of halogens. Chlorine trifluoride. That doesn't sound terrible at all. You know what to do. Draw a Lewis dot structure. And when you're ready to check, unpause the video. Okay, did you recognize that this was an expanded octet? It had to be. Chlorine normally, of course, has 3 lone pairs and a single valence electron and only forms 1 bond. But since chlorine had to be in the middle, it was the least electronegative, it meant it had to be forming 3 bonds. Gross. But remember to make sure that we've kept track of all of its valence electrons. Chlorine started with 7 valence electrons. But it formed 3 bonds, so it's used up 3 of those already, which means there are 4 electrons currently unaccounted for, so hey, I have to add 2 lone pairs to my central atom. Where? Wherever you can fit them. They tend to put them up at the top. Okay, so now there's our fun and exciting chlorine trifluoride. Let's figure out what the heck is going on. You know what? Why don't you try to figure out what the heck is going on? That's always fun. So you try these, and when you're ready to check the answer, unpause the video. Okay, first notice we have 5 electron domains, but only 3 bonding domains. So with 5 electron domains, you get trigonal bipyramidal. Now some people get really annoyed by this name. They're like, wait, 5, shouldn't it be penta something? Yeah. Well, notice first you've got tri and bi, which is 3 plus 2, which is still 5, and it's because you have 3 axial regions of electron density, and three equatorial regions of electron density, 2 axial. So they're the 3 and the 2 are in different locations, hence the name being a little bit weird, but still adds up to 5. Okay. Now, luckily, this actually kind of looks like the shape that it is. This might be one that you haven't used before, but it looks exactly like the letter T. And so we do call this T-shaped. Now for the bond angle, okay, you would expect something that looks like a T to have these 90-degree angles right here. But remember, 2 regions of electron density, and each one knocks off about 2 degrees. So that's why we would say this is about a bond angle of 86 degrees. Ta-da! Don't worry, we're going to practice this lots more in class, but you are now ready to move onward and upward to the next video, where we get to learn something fun and exciting, sigma and pi bonding, as well as orbital hybridization. It's going to be awesome. I'll see you there.